All right, here we go. This is physics reaction video number 33. Today, apparently, gravitational theory. So let's get it going here.
All right, so we're looking at lesson 28 today. We're going to be talking about gravitational theory. So hopefully after this lesson, you'll understand a little bit more about gravitational theory. I want you...
Hang on a second. What is TLW? The learner will. That's what I'm guessing. The learner will understand gravitational theory. Maybe? What do you guys think?
Understand a little bit more about gravitational theory. I want you to read your book, page 170 to 172, about gravitational theory. It's a lot of information that I just want you to kind of be familiar with. If you have any questions, I can go over it. But once you get to Newton's law of gravitation, you can stop. We're going to go over from there.
So this is really interesting, right? So they have this fantastic resource, whatever the textbook is, and to really clearly indicate that, hey, you know what? I'm assuming you're going to read these pages, and I'm going to help you a ton with the stuff after that. But of course, I'll help you if you have any questions. I really love that. I think that sometimes I've made the mistake where the textbook was just this thing that had homework problems in it. And oh yeah, I guess it has some sections in there that are useful, but I was more proud of my own exposition that I wasn't really leveraging the textbook as best I could. And of course, I've got a lot of buddies who are like, ugh, textbooks. Let's just have them work this stuff out. Which, you know, I'm fine with that. If you can really design that experience, then great. But I think that leveraging the text and really making it clear when you're expecting the students to read is really important. You know, the very first semester I ever taught, my chair came and visited me. And I actually was pretty proud of the lecture that I had given, and it was basically a lecture. I wasn't overly interactive back then. Come on, this was 2000. What do you want? So anyways, he came up to me afterwards and he said, oh yeah, that was really great. So that derivation's not in the book then? I said, oh, you know, it's in the book. Of course it's in the book. He said, well, so why did you read it to them? And, you know, that was the beginning of our conversation. And I think that I've really kept that in mind. Like, okay, the book is there. It's got cool stuff in it. How can we make use of it? And I love what she's doing here, which is like, look, read this stuff. I'm going to help you with the harder stuff that comes after that.
But just kind of read through about the gravitational theory. All right, so Kepler's law, just a little bit of recap over what you just read. The orbit of every planet is actually an ellipse, and the sun is at one focus of the ellipse. If you've talked about an ellipse in your math classes before, your ellipses have two foci. But
that's a really interesting question. Have you seen this in your math classes before? I mean, as I reflect on my own physics education, my own general education, I feel like I've spent way more time in physics classes talking about ellipses than in math classes, but it could just all be a mush right now. What I'm fascinated about anyone trying to do this type of lecture on this material is I'm so reminded when I teach this stuff that the people who developed it, or at least the names we attach to the people who developed it, were usually much more mathematically versed than our students are when they see it. And so there's a moment in this derivation, depending on what book you're using, where it says, oh, equation of ellipse, perfect. It's like they knew the equation of the ellipse. It was just part of their vocabulary. And when they were monkeying around with the forces involved, they're like, whoa, look, this is an ellipse. And yet I notice that when I do it with my students, it's this equation. They're like, yep, okay, what do I do with this? I'm like, oh, it's an ellipse. Like, if you say so, right? And so I think that it's really tough to leverage this stuff because the way it was first sort of developed, or at least the history we're told, right? That's always questionable. But it seems as though they were right there with the math. Yep. Oh, obviously an ellipse. Oh, this is really cool. Let's move forward. Whereas with our students, like, there's these two foci. You've probably never heard of that. Let me draw you something. I mean, ellipses are super, super cool, right? If you draw a string attached to these two and draw a string that's longer than the points between them, and then just kind of stretch out the string with your pencil and just go around, that's going to be the ellipse, which is super, super cool. It's a fantastic thing. I would love some advice. How do we work with our students just like she did? She's like, well, you've probably seen this in a math class, or maybe you've seen this in a math class, right? Number one, can you find that out, right? I mean, I guess you could ask the math teacher and say, hey, do you do this? Number two, do you trust that they're really going to know exactly the way you're doing it? Number three, should you use the same exact symbols that whatever math class did? Lots and lots of questions about that.
As a plural of focus. And then there's your ellipse. And it says that the sun is one of the foci. The line that joins the sun and a planet sweeps out equal areas in equal time.
Super cool.
So sometimes it'll move faster and sometimes it'll move slower. And you should have read that it moved faster as it was closer to the sun.
Cool. I love that you should have read. That's fantastic.
The square of the planet's orbital period is proportional to the cube of the semi-major axis of its orbit.
Sorry, I love Kepler's third law. Just seems to come out of nowhere. You cube this, you square this, and trust me, it all works out. It's so weird. I mean, it just comes out of nowhere. I think that let's see. The last time I taught this, now of course I didn't teach it to K-12 students or high school students. I was teaching it to physics majors. This was usually their third year, maybe even their fourth year of college physics. And you can get to 3 from 2 pretty straightforwardly from an algebra perspective, but whew, it's nasty. And I think that having students utilize these 3 things is cool. It's super, super helpful. The first one, awesome. The second one, super interesting from the perspective of Halley's Comet and things like that. It's kind of weird when thinking about summertime at the Earth, but the third one, I mean, basically we're saying, look, if you're out further, it takes longer. How much longer? So sorry about that notification. I don't know what it was. So I don't know. I'm really intrigued by this. There's just a ton of stuff you can do with this. There's really interesting things like, okay, well, we know from this that Mars is this far away. How long is its year? I mean, that's all you got to know. And you might think, oh, you can put a planet anywhere you want and shove it any way you want and have its year be any number you want. But nope, this Kepler's third law is basically saying you're kind of stuck. You get what you get. So I think this is really, really tough stuff. And I think that, people vacillate between, let me tell you the whole history of it and tell you all about all these people who did it versus there's just some straight math that's just chugged through. So I'm curious to see how she keeps going because I love what she's doing so far.
Those are his 3 laws that he came up with. So this is Newton's law of gravitation. F equals G m1 m2 over r squared. So G is your constant of proportionality. And he made a rough estimate of it. And it was greatly improved, but Newton did estimate it pretty accurately. In 1798, the estimate was improved by Henry Cavendish, whose unique experiment proved a value that was within.
So I don't know about you guys, but these dates take on new meaning if you really start studying history of something else. So our whole family is totally into Hamilton, the musical, and in Hamilton, of course, they have very specific dates they talk about, and you start to realize, wait a minute, Henry Cavendish was about the same age as Hamilton, right? Because clearly lived through the same things that you hear about in that musical, and to start to realize, wow, there's just so many connections in the world, because Mozart was alive somewhere in there too, right? And you think, oh, wait a minute, okay, powdered wigs, that's what we're talking about. I think that there's value just really sort of having context in these historical things. I don't know if we need to know when these people lived or were born and when they died. Maybe all we care about is when they did the estimate, right? So I go back and forth on the history stuff. Of course, one of the biggest problems is it just seems like it's a ton of white men, right? And so how do we deal with that? How do we think about it? I remember when I was talking with my buddies when I was in graduate school, a bunch of them were from China. And I said, boy, does it bother you that so many of these, math and physics things were discovered by white dudes? And they're like, well, and they would just give me tons of examples of things. Well, no, well, in China, it was discovered by this person, and we call it this. But I'm studying in the United States, so I guess I'm going to call it your thing. And I'm just fascinated by that. And, of course, nowadays, my goodness, look at the incredible internationalism of things like the Nobel Prize. Things, I mean, does terribly with gender, so let's I'm not forgetting about that. But as far as, different countries making contributions, different ethnicities, all that kind of stuff making contributions, it's kind of all over the place. Grab any old physics journal and flip through it, and I mean, I guess all you have is people's names, but they're not just all French and English dudes, right? So I think that that's great, but we have this sort of legacy that we have to deal with, and so I know that there are some people who are like, look, I'm just going to have my students discover this. I'm going to have them do this experiment. I'm not even going to tell them that some person named Cavendish did it, whatever it is, 200 years ago. I'm just going to have them do it, and then we're going to follow their law, and that's cool. But I think that as you study the history, you're also seeing some other connections that can be put to use. Then there's, of course, always the interesting applications that people have of things, right? And so, all of this Newton's Law of Gravitation stuff, people say that, it was always just to have their cannons be aimed better, right? Like it was for warfare. I mean, I don't know if that's true. I'm just saying that people will say things like that. And I think that the context can explain why maybe interesting pieces weren't further developed until later. So that's really, really cool. All right, let's keep going.
And 1% of the currently accepted value. So like I said, Newton was pretty close with his estimate.
By the way, I love this currently accepted value. That's better than the right value, right? I love that.
But this is the number that you need to write down. Probably put it on your formula sheet so you don't have to memorize it. 6.67 times 10 to the negative 11.
Teeny tiny number.
M1 and M2 are going to be masses, and R is going to be a radius or a distance. So we're going to use Newton's Law of Gravitation to calculate the force of gravity of the Earth on 3 different things. So we're going to use our formula that we just wrote down.
I really like part C.
Equals G
Oh,
M1 M2 over R2. Not R2, R squared. So for part A, our G is 6.67 times 10 to the negative 11. The 2 objects that we're looking at are a 1 kilogram mass and the Earth. And so you have to look in the back of the book to find the mass of the Earth. So turn to the back, go to like 7, let's see. Go all the way to the back and then flip forward 1, and it says planetary data. And so the mass of the Earth, it says, is 0.0598 times 10 to the 26. I want it in scientific notation, so I'm going to move it 2 places.
That's so cool. So you know why that planetary list has it that way, 0 point something, something, something. It's so that you can better compare the planets and maybe the sun. But I love what she's doing. She's like, that is such a weird way to do it. I'm going to move the decimal place over a little bit, which is ripe for errors, but to do it for your students once and get it right the first time, of course, is super useful. Also notice that there's no units in here. And again, the SI units are super, super interesting because if you can know that, okay, I'm doing everything in SI units, it's all going to work out, then you can say, oh, okay, yeah, let's see, this has a couple of kilograms in the denominator, so that's going to cancel these, and it's got a couple of meters in the numerator, so it's going to cancel these, and all that's left is a Newton. Yeah, okay, so I'm good to go. So then you can just plunk in, that's fine with me. I also love that, we got this weirdo number here, and then you got a 1 here, and then you're looking something up in the back of the book, and it's just this monster number, this huge, gigantic mass, and you're thinking, oh, this poor 1 is going to get dominated, but it's multiplicative, it's not additive, right? So it doesn't get dominated, it plays its role.
So 5.98 times 10 to the 24th. And then over the radius. So the radius is going to be the radius of the surface of the Earth on this one. So you're still looking at that, the back of the book, the table, and the radius of the Earth, it tells you is 6.37 times 10 to the 6th. So we're going to square that. So now you've got to plug that into your calculator to get your answer.
I love that we can hear the clicks of our calculator. I was frowning because whenever I think of the radius of the Earth, I have 4,000 in my head. And I'm like, what, 6, what? And it's because I have 4,000 miles. That's just the number that I have in my head. And it's a nice round number, and it's roughly right. And I think that 6.37 times 10 to the 6 doesn't mean much to people, whereas 4,000 miles has a meaning, especially when you think about the width of the United States, right? So 4,000 miles, I think the width of the United States is like 3,200 miles or something like that. So take the United States and go like this, and that's how deep the Earth is. So there's times when I really want to have numbers that I'm going to remember, and I guess 6 million meters I could remember too, but for some reason I get stuck with the miles, of course. But if I do miles, then I gotta convert everything. So there's this trade-off, right, of wanting to figure that kind of stuff out. The other reason I like miles for the Earth is that it's about 25,000 miles, 25,000 miles around, which tells you that on the equator, every time zone is about 1,000 miles. So that's just nice, round, gorgeous numbers to remember. Every time zone is in the vicinity of 1,000 miles when you're on the equator. It's super easy to remember, but then you're stuck in miles. And if you ever want to do calculations like this, you constantly have to do the conversions. And when things are squared, the conversion just gets nastier, right? So having a table in the back of the book is super useful, but I find that remembering that driving around the world would be 25,000 miles is an interesting, useful number to remember. In fact, I remember seeing a billboard once after I passed a restaurant. It said, such and such restaurant 25,000 miles ahead on your right, which I thought was just great, because for a ton of people, they're going to be like, huh? But I loved it, right? Because it was a number that I recognized. Clickety clack on the calculator, but it's great, right? Because she's taking the time to do it. Recognize it. The students have to say, okay, I better do this too. See if I can beat her, right? Let me race. See if I get the same answer. And of course, the other really interesting issue is that we know the answer. We know the answer. It's 9.8, right? It's going to be 9.8. Which is so cool, because the students are like stuck in this. Oh my God, this is so weird. I don't know what I'm doing. I have no idea what to expect this answer. But just imagine the look on their face when they plunk all this ugly stuff into their calculator and they get 9.8. Surely that's a number that's going to jump off the screen for them, right? So I'm curious to see how she deals with that.
Okay, so we're only going to go to 2 sig figs because that's how many they give us.
Ugh.
So you should get 9.8. And then our fourth is in newtons. So newtons would be your answer. Okay, now we're going to do B. So the only thing that's going to change on this one, the gravitational number is the same.
So what's interesting about going from A to B, C is going to be the tough one, but from A to B, right, if everything really is the same, the question that I have for you guys is, should you just tell your students, just multiply A by 100 and you're done? It's 980, the end, right? Or should you do what she's doing, which is to say, look, we can always go back to this. It's always going to work for you. Just be careful. You write your G and then your M and then your M and then your R squared. And trust me, you'll get the right answer. So that you might use the fact that, it's just 100 times the previous answer as like a double check, right? So I really find that really, really interesting, especially with these students who are just seeing this stuff for the first time.
It is the 100 kilogram mass instead of it being a 1 kilogram mass. We're still dealing on the surface of the Earth, so that's going to be the same, and the radius is going to be the same.
So I'm going to fast forward her plunking in the calculator here.
9, 8, and we only have 2 sig figs here, so 980 newtons.
Nice.
So that would be your answer there.
All right, so part C is the really, really interesting one.
Now we're going to look at...
And part C is interesting because if you ask students this in a variety of ways, they will tell you the answer is 0. Right? So at first they're going to be like, okay, I've just plunked some things into my calculator, I'm going to get an answer. No. Get them to say, okay, this is like space station height, right? Like the gravity on the space station. 0, right? 0, done. I don't even need to do this calculation. It's 0, right? And so I love part C because it's going to end up being, I don't know, 9.2 or something, right? It's going to be something basically not that much different than on Earth. And it's cause for such great conversation, I think. So I'm curious to see if she has the time to do that today. I'm looking at the timing on her video, and there might not be enough time to really drive that home. So I'm just curious to see.
Part C. Again, your G is 6.67 times 10 to the negative 11. We have a 1 kilogram mass.
I'm just thinking about the students following along who are like, yeah, I got this. I'm cruising, and they'll put a 1 there, they'll put the 5.98 next, and then they'll divide by, what do I put for the radio? Oh yeah, 6.37 times 10 to the 6, right? So I could just imagine a student plunking away and getting exactly the same answer as A, like same exact number out of their calculator, and not realizing how to use the 250 kilometers. Notice that it's kilometers. Ugh, they gotta convert that, right? So I just love this question.
And we have the mass of the Earth. But now the radius is different. So it's the radius of the Earth plus the part that we are above the Earth's surface. Now I'm going to go back to the chart real quick in the back, and the radius was in meters, and they told us this was not in meters. 250 kilometers, 1 kilometer
Love it.
is 1,000 meters.
Love it.
So you have to multiply it by 1,000. So 250, and then 3 more zeros, so 250,000.
Love it. Squared.
That's what you're going to add to whatever radius the Earth.
And you can see that, right? So it's funny to write these two in this way. Like this one, you can kind of get a real sense of how big it is, and this one, and when it's not written in the same way, you're not sure. Well, boy, that's going to be a big change. Well, no. If you write this out, it's basically 6 million. So so not this digit, but this digit here, right? So imagine a 6 right next to it. So this is 1%. 1% change would change this digit. So this is like a 10%. If this were a 6, this would be a 10% change. So this is like a 3% change, but it gets squared, right? So this is just not that big of a change.
So now we're going to plug that into our calculator.
I'm just going to fast forward till she writes it down.
And go to 2 sig figs, you're going to get 9.1
Hey,
newtons.
that's pretty close. Like, what did I say, 9.2?
So that's how you use that formula. It's not terribly difficult. You just have to make sure that you're paying attention to all of the information they give you.
Love it.
Okay.
All right, so I'm just going to stop right there and just point out some of the great things that she's doing. So obviously the reading the book stuff was super, super great. I loved that. And then the way that she worked this problem, which is absolutely saying, look, you guys, just trust me. Just use this GMM over R squared. It's going to work. Let's see how we're doing. Let's get familiar with this and start to really feel like we can trust ourselves. I think that she's really set the table for a future conversation to say, hey, guys, remember back when we did part A and we got 9.8? Did that surprise you? Right? Well, we've been doing that already. It's the same old stuff we've been up to. And then, hey, did you notice in part C, we didn't get 0. We didn't even get teeny tiny. We got 9.1. It's pretty close to 9.8. So what the heck's going on the space station? It's really setting the table for some really, really great conversation. All right, everybody. Thanks so much. Have a great day. And remember, physics teachers are awesome.